Hello, everyone. How are we doing? We can do better than that. How are we doing? Hey! Okay, great. Thank you all so much for coming to my talk. It is a real privilege to be here in front of all of you, showing the things I've been learning over this year. So yes, thank you very much. It's great to be here. So what I'm going to be sharing with you is composing. It's a slightly funny sounding title, Composing Ancient Mathematical Knowledge into Powerful Bit-fiddling Techniques. Hopefully, it sounds like some of you found that intriguing and some of you are here, so thank you for coming. So what I'm going to be sharing with you are new insights from the ancient Egyptian multiplication algorithm that we've used to give us the freedom to synthesize operations that you might not have in your hardware. And we've been able to get some great performance doing that. And the caveat is that your operation can be expressed by the repeated application of some associative operation. So in particular, we'll show off how we've implemented this element-wise parallel multiplication for like arbitrary widths of arbitrary lanes. And we'll come on to that later on. So first things first, I'd like to give an enormous shout out to Eduardo Madrid, who sat here at the front, and our friend, and collaborator, Scott Bruce, who both incredibly talented, bright software engineers who have taught me so much over the last year. So I'm incredibly grateful to both of those two. Who am I briefly? My name is Jamie. I'm a developer at Make It, and we're a music tech startup based in Los Angeles. I write lots of different code. I do lots of C++ for our audio engine, a bunch of C++ for like neural inference code, a bunch of different things. I got my master's from Queen Mary in computer science, and my BA, funnily enough, is in music. So a bunch of the inspiration for this work came from our reading of the Alexander Stepanov and Daniel Rose book, From Mathematics to Generic Programming. A lot of the power of generic programming is we've leveraged to get the work done that we've done. And as I said before, the technique of the ancient Egyptian multiplication is at the core of this, and it's the leveraging of the power of associativity and repeated associativity that is at the core of this. So associativity is very important to the world. Furthermore, repeated application of associative operations is everywhere in the world. You just have to look, and you'll see it. For example, the finite field exponentiation or modular exponentiation is used as it's kind of the beating heart of a lot of the public key cryptography that we use. So RSA, the Diffie-Hellman, and we can implement this using the repeated application of some associative operation, like modular multiplication. It's kind of fundamental to the functioning of modern digital life, like cryptography in general. We've used these techniques for, as I said before, the implementation of parallel multiplication for our SWAR library. And don't worry if you don't know what that means, we'll touch on that later. Some of you may have seen either Scott or Eduardo's or I's talk before about SWAR techniques. So we'll come into that later. And furthermore, like another motivation for this type of work might be to look at CUDA. And CUDA doesn't have a primitive for integer exponentiation. There is one for doubles, but there isn't one for integer exponentiation. And my aspiration is by the end of this presentation, you should have a reasonable idea about how you might implement your own implementation of integer exponentiation for CUDA. Hopefully that sounds exciting. Hopefully that sounds interesting to you. That's what we're going to be exploring. And all of these subjects sound very disparate and disconnected. And so how do these all connect? And why are you talking about Egyptian multiplication? How do these things connect? And really, we're going to be using the Egyptian multiplication as a lens to understand and to, as the main tool to see into how this generalization works. So a quick maths briefing. We talked about associativity, and there's this whole idea of commutativity. And I just want to clear up these two concepts. So commutativity is the idea that the order of the operations that you do them, it doesn't matter. We'll note here that the semantics here are slightly ambiguous. So let's have a look at associativity. Associativity is all about the grouping of the operations. Doesn't matter, you'll still get the same result. So you'll see that we can do the C and D first, and then the result of that will do that. The ordering is still important, but the grouping doesn't matter. And we can use that property in a way to, that's kind of at the core of how this whole repeated application of associative operations, we're able to transform things which might be linear time into a log 2 time, a log n time. So as I said before, we're going to understand all these complex transformations through the lens of ancient Egyptian multiplication. So what is it? How does it work? It's how you might multiply something. It's a very simple algorithm. And just roll with me here. Everything will become clear. So the algorithm is pretty straightforward. We have a result. We'll start there. Just initialize it to 0, which is the identity, the neutral element for addition. And if our multiplicand is, or our multiplier is odd, then we'll add our result. We'll add that to our result. Well, I'll come back to that, this break clause in a second. And then we'll double our multiplier, and then we'll double our multiplier. If b equals 0, thank you. That is a typo. So if b equals 0 here, if our multiplier is 0, we've consumed all of our multiplier, then we'll exit. And if you didn't quite follow that, don't worry. We'll have a nice spreadsheet worked example. So hopefully this will come straight up. OK, great. Gotta love a spreadsheet. It's like the world's greatest calculator. So for example, we have our multiplicand and our multiplier. And I've implemented the very simple logic to do this algorithm. So if our multiplier is odd, that's the logic in here. And once this gets to 0, that's where this terminates. So that's our result. So 39 times 45 is 1,755. I'll prove that to you. 39 times 45. Wow, OK. But what's pretty cool about this, and you might have noticed this thing off to the side, this is the linear time version. And this is where it stops. So look at the saving of number of operations we can get. By leveraging the power of associativity, we've cut this down to just a few operations. And you think, OK, we can do that for multiplication, sure. But what we're trying to drive home here is that you can get this benefit for any monoid. Any monoid, you can get this type of optimization. So hopefully, by the end of this presentation, you'll be convinced and feel empowered that you can do that too. OK. So I wanted to just go one step deeper to show off what's happening under the hood of this algorithm. So you can see, as we're testing for odd, what we're really asking at the integer level is the least significant bit of this number 1 or 0? And if it is, if that bit is set, if that number is odd, then we should do the thing. We should add the number to itself. We should add the square. Because each index of the binary number represents some power of 2, some square, some power of 2 multiple of our multiplier. And that's really the fundamental way that this algorithm works. So let's have a look at this in C++. We're at a C++ talk conference after all. So hopefully none of this is going to blow your mind. We start with our result. Start with 0. If the LSB is on, if the least significant bit is on, and that is some jargon that I will come back to, and hopefully you guys can roll with, is the least significant bit and the most significant bit being on or off of a. Hopefully that makes sense. So if the least significant bit is on, if it's odd, perform the operation, and then we go around, we double, and we consume the least significant bit. And then if we've consumed all of the multiplier, then we break the exit. And then return the result. Here's the thing that we really are interested in sharing with you, or one of the things we're very interested in sharing with you, is that, yes, you can test for oddness, and you can pass this count, this binary number, from the least significant bit first. What's to stop you starting at the most significant bit and going the other way? Far as we can see, far as we've researched, no one has done this before. This is a novel technique for doing, for like passing these counts and performing these associative operations. By the way, we're going to use this term associative iteration. That's what we've kind of called this technique. It's a new term that we've coined, so you won't be able to Google it yet. Maybe soon people will start using this term. And so yeah, that's a credit to Eduardo and Scott for having coined that and had come up with that very useful label. So this is what we call the regressive way, when you start from passing the most significant bit first. And you'll see if you go back to this example, we've got the example of 177. And we'll use that same example again. So if you look here, we've got 3 bits of memory, or 2 bits of memory, the result and the square. But here, we've only got the result, because the algorithm is slightly different. Because we don't keep track of the square, the difference is we always double our result every iteration. And if we have a bit set in that most significant bit, then we add 1 multiple of input. This is the algorithm. It's slightly different. Hopefully we don't need to go over it too much. The main difference is, between these two, for the most significant, for the regressive way, you need to pass every single bit of your count. Whereas in the progressive way, once your count is 0, you exit early. But with this way, you have to do the whole count. So there's a trade-off there in terms of like memory usage and performance. And there are some caveats even there, but we'll come on to those later. And we talked about the trade-offs there. So noting for the regressive way, it uses a third the memory, which is the cool thing. OK, great. We've learned how to multiply integers. Thanks for coming to my talk, everyone. Wasn't that fun and interesting? OK, great. We learned a very roundabout way to multiply integers. I think we can do more. I think we can go more general. I said that this applies to all monoids. Let's see how we can get there. We've looked at this Egyptian multiplication. How can we generalize this? So we have some operation that we're doing in the case of multiplication. The operation that we're doing is addition. It's repeated addition. And we're doing it some number of times. So this is an intermediary step I wanted to show you to start to show how we generalize, at least the regressive way. So we have our iteration count, which is the number of bits in the type. We have our result. We're going to initialize that to 0. And we have our operation, which is if the most significant bit is on, do the addition right here. If not, just leave it alone. We have this idea of the count halver. And we use this idea of a count halver for the regressive and the progressive way. This is technically doubling the number, you can see. But we haven't yet found the right perfect name for this. So this is what we've got so far. And you can see we've abstracted the operation into 2 places now. As opposed to doubling, explicitly doubling the result, we're doing the operation, we're adding the result to the result. And we have to feed it a count to the operation. But in this instance, we need to give it a count that will always fire the operation, if you like. We kind of struggled with the name for that variable too. We used to have it called four-squaring. It took me to writing these slides to realize what exactly that was doing. So the variable for the most significant bit of the type being on, that will always fire the result. And that will always double the result on that line. So hopefully if you followed the last slides and you can follow more or less what's happening here, there's not too much of a jump here. We're still just multiplying 2 numbers. And this is, if you look at the previous slide, this is the template that we've written that encapsulates the same logic for all monoids. So hopefully, if you're able to follow this for multiplication, this is the code that applies for all monoids. So we start with our neutral, the identity element. If our iteration count has run out, then we exit, we do our result. Hopefully you can kind of follow that. So now we can use this stuff. And you think this template looks a little bit nuts, why would we use this? But what's cool is that when you use it, there's only a handful of bits of information that you need to bring along. You need to know what your identity element is. You need to know what the value is of the count that will always fire your operation, your four-squaring. You're still getting there with the naming and the concept. And you need to know your operation, and you need to know how to halve your count. That's all you need to know to get multiplication. And if you wanted to do exponentiation, let's say, the cognitive overhead for doing that is basically nothing. You need to know that there is a different identity element, because the fundamental operation now is multiplication. The identity is 1. And you need to tell it that you want to do multiplication when the MSB is on. That's it. So hopefully you can see how you can compose your associative operations using this template in a very nice way. But hold on, you say, we're still only doing things for just integers. That's still a little bit boring, maybe. OK, we'll come on to that. We'll first show you that the template works. So we have this like hand-rolled Egyptian multiplication, and we have the Egyptian multiplication that uses the template. So we have the one that uses the template, which is here, and we have our hand-rolled one here. And we instantiate it with some concrete types. And they have exactly the same assembler. Hopefully you can convince yourself of that. The output is the same. So hopefully you say, OK, this template is making clear to the compiler that, like, what's going on here. So OK, maybe it works for concrete types. Does it work for other types? Ooh, go on. Come on, technology. I believe in you. But the technology believes in me today. All right, we'll close the window. We'll open it up again. All right. Cool. We were roughly here. OK, great. So this is just integer multiplication still. So can we do this for other types? We mentioned about SWAR. SWAR is effectively a software SIMD library that Eduardo, Scott, and I have been working on and developing. So you might have seen some of our previous talks. Anyone seen any of the SWAR talks? Or familiar with the? Yes, some hands up. You guys might be familiar. OK, so I put these slides in here for give you guys a briefing on SWAR, just so you can follow along with the rest of the things I'm going to say. So you guys familiar with SIMD? Hands up for, OK, we're happy with SIMD in general. So SIMD, you got a bunch of data. You're doing one instruction. Generally, people think this requires some kind of specialized hardware. We're here to say that it doesn't. So SWAR is basically using general purpose registers to do SIMD. So you pretend that you have lanes. Say, hey, I know there's not really a lane there, but I'm just going to pretend that these are 4-bit wide registers. I'm going to add them together and have a lot of fun doing it. The caveat here, of course, is the fact that you might get overflow. Oh no, this lane overflowed into the other one. What can we do? You just have to be aware about that, and you implement your operations in a way that is safe for lanes. So you have to implement your operations in a way that is safe for lanes. Surely that's going to be like prohibitively expensive to do that. It turns out it's not. You just need a few masks, bitwise ands, shifts, and the overhead is incredibly low. So you get a lot of performance benefits from doing this parallel work, and very little overhead for doing the maintenance and the housekeeping to keep all your lanes in order. So this is like, just to show you quickly like what the library looks like. You have this SWAR type. You define how many bits for each lane and the underlying type. So here you'll have 8-bit lanes in the 64-bit type. And I've written this one out in hexadecimal so you can see all of the 8-bit lanes. So you've got 1 and 2 and 3 and 4, adding to 1 and 2 and 3 and 4. And then the result is 2, 4, 6. And in the last lane is 8 plus 8 in hex is 10 because hex. And I promise the static assert isn't red and squiggly. And you can check out the repository here at the cpp.zoo/zoo if you're interested in this sort of stuff. So back to associative iteration. This is the regressive way. If you remember the previous slides, hopefully this looks pretty familiar. We have our iteration count. We have our neutral. And bear in mind, this neutral is now lane-wise. It just happens to be that all the lanes are 0, so that's the way we can initialize that. Our 4 squaring, which is the most significant bit set, is going to be the most significant bit set in each lane. And I mentioned before that when you're doing the regressive formulation, that you have to pass through every single bit. We have set up this template so that if you know ahead of time your count is going to be small enough that you can only do a handful of them, you can say the actual number of bits is only this much. So you can exit early, shift your things correspondingly, and get a little bit of performance boost. And that's a lot of the philosophy of the library is, if you're able to get extra performance, we will give you the levers to do so. So the operation still looks very similar. You need to make a mask from the MSB. And basically if the MSB is on, we'll create a mask for that lane that will allow that through. When you AND it in and then do the addition, that's the addition, but lane-wise. And then the repeated addition lane-wise is how you get lane-wise multiplication. And just composing all these together, this is multiplication for this parallel multiplication. This is all you need to know and to understand to do parallel multiplication. And it was in generating these slides that we realized that we'd updated the library and we were able to abstract this shifting even more tersely. And I think we could even do better by calling this something like consume most significant bit, and it will just do the shifting safely for you. But that's just to say that this is a library that we're actively working on right now, and it's always growing. And if you feel inspired and you think it's interesting, come contribute. It's really fun and interesting. So, as we did exponentiation before, let's do it again. It's very similar. It's not that much more complicated. The thing that's a little complicated is you have to understand a little bit about the masking and what that means, but it's not that hard. You have the iteration count. Our neutral now is lane-wise 1, so the least significant bit of each lane being set to 1. Our 4 squaring is the same, the shifting is the same. Operation is slightly different now. We still create the mask in the same way. We do the multiplication for every lane still. And then this logic is figuring out whether this value that we just calculated, should we continue to add that in? We don't need to go too much into the details of ANDing in, ORing in each lanes, but suffice to say that this is all you need to know to do lane-wise parallel exponentiation. So the thing that is interesting about these regressive and progressive formulations is that they don't necessarily give you the optimal path to the count. And for example, 15. Say if you wanted to multiply something by itself 15 times, it's not going to give you strictly the most efficient path there. So this is the progressive way. You're going to end up with, I think it's about 7 additions. Yeah, if we write it out in, we unwrap this C style, you're going to get about 7 additions. And in the Stepanov and Rose book that we mentioned, they point this out and they say, you could do that in only 5 additions. You say, okay, that's very interesting. And the thing that's interesting, I think that book was written at a time when people might be worried about, we need to get rid of an instruction here or there. At this point, the compiler can kind of see right through the addition chains that are going on and be like, look, I see what you're doing. we don't care. I see you're multiplying by 15. I'm just going to do this for you. And it's going to use the load effective address. And I think what is interesting here is that, and the compiler is kind of highlighting to us here, is that instead of strictly doing
multiply by 15 directly because it's going to be the same assembly. Manually multiply by 15.
Oh, okay, sure. Yeah, that's a good idea. Return. Yeah, there you go. So your compiler, you don't need to, your compiler is pretty smart these days. So I think the insight that we think is interesting here is that maybe you don't necessarily just need to do addition chains. What if you were able to do chains that were load effective address chains or multiplication chains, or you were able to a priori know something about the chain, the chain that you have, whether it's going to be a set of load effective addresses or additions or multiplications, and you're able to compose that in a way that's going to get you the best result. Okay, interesting. Okay, so touching on before, what's very interesting is that we're able, okay, I'll let this load up. Okay, so on the compiler really being able to understand this code and these templates and see through the addition chains, we're on this is like maybe a little bit much to look at. But we've got our multiplication function that we looked at before. This is the exact same one. And we're asking the compiler to figure out, we want to do four lanes, each 8 bits wide for this 32-bit type. We want to do, in this lane 7, in this lane 14. I promise that's 14. And these 2 lanes are going to be clear. And we're going to do this multiplication. We give this compile time constant of lane-wise constants. And what's super interesting is that, we'll break this down in a second on the next slide. This is generating assembler that is doing the addition chains for both lanes simultaneously. And just suffice to say that I won't bring it up later. If you try and do it more manually, like a human programmer might try and do something like this generates more instructions. Using this template makes it more transparent to the compiler what you're trying to do through the use of associative iteration. Okay. It doesn't like it when I change back. Okay, interesting. Maybe something about the full screen mode. All right, good to know. Right. So this is exactly what we had up before. So the first 2 instructions are clearing the lower lanes, and that's it. And then you can see we're using the load effective addresses in order to, in each lane, and like synergistically preserve the lane-wise multiplication. So you'll see by the end, the top 2 lanes are being multiplied, the more significant lane, which is non-zero, multiplied by 7, and the lower lane being multiplied by 14. And hopefully I've been able to get across how mind-blowing that is. The compiler is able to see addition chains lane-wise through this template, if you give it a compile time constant. I think when we were first discussing this result, it was like, oh my God, how is it able to do that? It seems like if you tried to do this by hand, that would take you forever. And the compiler, when you don't use the template, doesn't produce this result. It uses more instructions. So this is the result I think we're particularly proud of in terms of you're able to leverage this power of this template and get very interesting, efficient results. So hopefully we've been able to get that across, how cool we think that is. Future work we're interested in is also in the realm of examining the chains. So, for example, evaluating polynomials. So when you're evaluating a polynomial, you're going from different exponents. You might go from, have x to the power 2, and then 3, and then 601, and then 3,000,002. And you've kind of got this chain. But you want to get to 3,000,002, but you need to make pit stops. So in the future work we're planning, you can might be able to express the addition chain that takes pit stops via other numbers in order to evaluate polynomials. So you can use associative iteration to evaluate your polynomials, which I think will be very, very fun. So associative iteration is more general than SWAR. It is as general as monoids. This applies for all monoids. So hopefully you feel maybe slightly convinced that associative iteration can be used to implement primitives that aren't available on your platform. For example, if you haven't got your integer exponentiation, hopefully you can feel convinced that you might try this technique to do that. Or if you have some other platform and there's not something available like a population count and you want to do it lane-wise, that's something that we've done. You can try using this technique to do that. So any monoid you have, think about what you're doing with it. Can you use this technique? Maybe, probably. You might be able to get some performance wins. So maybe you have some matrix multiplication you want to do. Many operations on like quaternions might form monoids. So any monoids you have, see if you might be able to apply this to them. If you guys have any questions, I would love to take them. And thank you so much for your time. It's been a real blast talking to you guys. Hello.
At the core of your basic technique is a modification of Newton's method of evaluating polynomials that's applied to do multiplication. So starting at the most significant bit, you're representing the left operand as a polynomial. You're evaluating at x equals 2 with binary coefficients. But the modification, which I've never seen before, is to, instead of starting at 0, which is what the traditional algorithm is, you're starting with a value y, which is the multiplicand on the right side. And you end up, after you do Newton's method, you end up with the product of the two numbers. You've decomposed one into its bit form, but you haven't decomposed the other one at all, which means that you can take the left operand, or the right operand, and basically make it anything you want that is in associative algebra. So your idea of doing matrix multiplications will definitely work with this because the underlying math has been known for quite a while.
That's amazing. Thank you so much for sharing.
So for those of us that want to play around with this, what are some good things that we can do to use it and play around with it rather than trying to reproduce the things that you've done? Is there a list of, a handful of things that you think this would be really applicable to certain things, hashing different things that it might be really applicable to that we could start playing with it?
Like what would be a fun project to get started with this doing that we haven't done yet? I think the CUDA exponentiation would be a great place to start. I think division. Yeah, you might want to try and do division. Yeah. Yeah, chain subtraction, yeah. Maybe division. SWAR division, that would be a really valid, at least for if people are interested in contributing to the zoo library, SWAR division, potentially.
Thank you.
Any other questions?
Oh, I'm sorry. I project and not that much all the time. One of the applications that would be, I think, fairly low-hanging fruit for at least a trial on this is to try to parallelize 8-bit FFTs into
I
a
would
64-bit
love to do
thing.
FFTs. That's
Because I think you've got the essentials of what you could get a fuse multiply add into your basic model.
yeah.
You need 2 input streams rather than 1, but I think that's the only major modification you need.
Yeah, I mean that's one of the things I'm very excited to do.
And not only that, but rely on the hardware if fuse multiply and add is available.
Yeah, there's some interesting stuff to be done here. But the other things, I think you may be able to do convolutions on pixel arrays with low bit counts using the same kind of technique.
Mathematical knowledge to the very forefront of the
But do go read up on Newton's method, because I think you're going to get a lot of insight about how to do more general stuff by looking at just how that works.
Yeah, Newton's method. That sounds amazing. Thank you. Yeah, I'm very excited. I do audio stuff. There's a bunch of audio people, I think, in the crowd. So FFTs are like right at the top of the list of things that are interesting to me too. Great. If there's any more questions, no more questions? All right. Thank you very much for your time. I really appreciate you guys. Thank you so much.